Hello everyone, we are starting a new topic just now, and this topic is called integration. So it's basically the second part of an overall topic called calculus, and the first part we've studied in a fair bit of depth, that was differentiation. We're now looking at integration, and the two topics are really closely linked. So let's start off by thinking about how integration compares with differentiation. If you remember, differentiation was a branch of calculus. We used it to figure out the gradient if we had a curved line, so we could find out the gradient at any point on any given function. The rule we used was that if we had a function f of x equals ax to the power of n, then the derivative, using this notation, f dash x was an times x to the power of n minus 1. We're going to try and come up with a similar rule for integration. It says here that integration is a branch of calculus used to find the area underneath a curve, provided we know the function. Ignore that for just now. We've kind of had to do things in a slightly different order since we're working from home. So we're going to come back to this later. For just now, we're just going to think about integration as being the reverse of differentiation. Okay? So let's look at these two things in a wee bit more detail. So this rule here, if f of x equals ax to the power of n, then the derivative equals an times x to the power of n minus 1. What we have actually done is, the first thing we do is we multiply the function by the power, and then the next thing we did was we subtracted 1 from the power. And that was the two steps basically involved to carry out differentiation. We multiplied by the power, and then we subtracted 1 from the power. And that took us from a function f of x to a function f dash x. We're going to look at how we get back from a derived function f dash x, how we get back to the original function. So we'll break that down a little bit. Again, we're going to do the reverse of that whole process. So remember, when you reverse something, as well as reversing the mathematical operations, you need to reverse the order that you did them in. So we're going to start with reverse and subtracting 1 from the power. So the reverse operation is going to be to add 1 to the power. That's the first thing we're going to do. So that's this added 1 to the power. And then we're going to reverse this multiplying by the power. So the opposite of multiplying by the power is going to be dividing by the power. But what we need to remember is, because we've done it in a different order, we're actually dividing by the new power. And that is really important. So we've added 1 to the power, and then we have divided by the new power. The new power was n plus 1. So we divide by n plus 1. And that is the rule for reversing differentiation, a process that we call integration. Sometimes it's called anti-differentiation, but basically, if we start from a function f of x and we differentiate it, brings us to f dash x. If we want to go back the other way, if we've got the derived function f dash x, then we can do the process of integration in order to find the original function. There's a couple of bits of notation you need to get used to, and the notation looks a little bit strange. To find the original function f of x, we need to integrate the derived function with respect to x. That's what those 1, 2, 3 distinct pieces in the notation mean. The first one is we are integrating. The second bit is what we're integrating. So we're integrating the the derived function, and the third part tells us what we're integrating it with respect to. And that'll make more sense as we do some examples later on. Using the alternative notation that we had for differentiation, instead of speaking about f of x and f dash x, we could speak about y and dy by dx. So in the same way we can apply that notation, and we can say to find the original function y, we need to integrate the derivative with respect to x. Okay, let's look at that in a wee bit more detail, because unfortunately it isn't quite that simple. And to try and illustrate that, we're going to consider these three examples here. We've got three really similar functions. The middle one is y equals x squared, just a really simple squared function giving us a quadratic graph. The one above it is x squared plus 5, so it's just exactly the same shape of graph, it's just been moved up 5. And the third one is the same shape again, but it's been moved down 3. If we carry out differentiation for each of those functions, hopefully you remember how to do differentiation, but we are just multiplying by the power and taking 1 off the power. Then for the first one we get 2x. Remember, the derivative of this bit is just 0. This one here is just going to be 2x. And the third one is going to be 2x as well, because when you differentiate a constant term, like the minus 3 or the plus 5, then the derivative of that bit is 0. So all three of these functions have got exactly the same derivative. And if I was to draw a graph of the derivative, so it's a graph of x against dy by dx, then I'm just going to get a straight line graph. Okay, so when we differentiate each of those three slightly different functions, they give us the same answer. That causes a little bit of a problem if we want to try and think about how to reverse this process to get back from here to the original function, because clearly it's not going to be very easy to decide whether it takes us back to this one or this one or this one. Let's look at it in a wee bit more detail then, again. So we're going to try reversing that process. So we're trying to get back from this function to find out what the original function was. So this is a derived function, dy by dx, which is just 2x. If we integrate it, so that means we are going to add 1 to the power and divide by the new power. There's actually a little bit of a mistake in the note here. There should be a 2 in front of there. So when we add 1 to the power, it goes from 2x to the power of 1 to 2x to the power of 2, and then we divide by the new power. So we're dividing by that 2 there, which gives us x squared once you cancel out the 2 and the 2. So it's taken us back to the function y equals x squared. But what happened to the function y equals x squared plus 5 and y equals x squared minus 3? We need to adapt our function, our rule for integrating, so that it can bring us back to the correct function. And in order to do that, what we actually do is add a c on the end of it, and that is called the constant of integration, and we use that when we're working with this kind of integration. And we'll get to different types of integration a bit later. But anyway, you can see what that means as we do some examples just in a second. Here's some examples we're going to look at. Let's just move this down a little bit out the way, and we will focus on these ones to begin with. Okay, so we are trying to integrate the following derived functions to find the original function. It says leave your answer with the constant of integration c at this stage. So that's all we're doing just now. Later on in the task we'll be looking at how we figure out what c is, but we're not doing that today. So we are For question A, we are going to integrate x to the power of 5 with respect to x in order to try and get back to the original function. I think I should maybe change my notation slightly. I'm going to just change that a little bit. We are trying to figure out what the original function is, and it is going to be the integral of x to the power of 5 integrated with respect to x. So when we go to do that, we're just using the rule, which was add 1 to the power, so it becomes x to the power of 6, and then divide it by the new power, which is 6. So the answer is x to the power of 6 divided by 6 plus c. That's what the new function is. That's what the original function was, rather. Let's look at example B. The question said use it to find the original function. So the original function is f of x. We are going to integrate 8x cubed with respect to x. Let's do that. So we've got our 8x. We are adding 1 to the power to make it 4, and then we're dividing it by the new power, which is dividing it by 4, and we need to remember to add the constant of integration c. And we can simplify that just to finish off that question to say that the original function is just 2x to the power of 4 plus c. And as I said, we'll look at later on in the topic how we figure out what c is. Question C, this time it's a slightly different notation, but it doesn't matter. In these examples, because I've had f dash x, I've gone for f of x. In this example, I just see I've made a little mistake actually, because this one was g dash x. I should have actually, so you better fix this if you're doing your notes at the same time, I should have actually made that g of x, and that's the kind of thing that the SQA would pick up on if they're marking papers. You'd lose a mark for doing that. The notation needs to be consistent. For this one here, example C, we're moving to the derived function is dy by dx, so we are trying to figure out what y is this time. We're still going to integrate the function minus 4x to the power of minus 5 with respect to x. This one's a little bit trickier because it's got that negative index, but we can cope with that. We are going to take our minus 4x, we're going to add 1 to the power, so just be careful here, we're adding 1 to minus 5, so minus 5 plus 1 takes you to minus 4, then we're dividing by the new power, and we need to remember to add c. And of course we can finish it off by simplifying it. Minus 4 divided by minus 4 cancels out to give us x to the power of minus 4 plus c. Okay. Now we could take this example a little bit further and get rid of the negative index and all that kind of stuff if we wanted to, but at this point we don't really need to. But we could have changed it to 1 over x to the power of 4 plus c. Okay, we're now going to look at some slightly different examples, slightly trickier I suppose because they've got some fractional indices and the notation is slightly different, but the maths we're doing is exactly the same. Okay, so we're going to look at these 4 examples here. This time it doesn't have all the stuff about finding the original function, etc. It's basically just asking us to integrate these functions. So let's look at the first one. You can see yourselves that we're trying to integrate 8x to the power of minus a half with respect to x. So we need to take our 8x, we need to add 1 to the power, so minus a half plus 1 makes it go to a half. We divide by the new power, and then we add on our constant of integration, the plus c part. So that's just made a good start to that. Probably enough to get a mark at this point, but we still need to finish it off. of course we need to find out what 8 divided by a half simplifies to. That's kind of okay to do in your head. How many times does a half go into 8? It goes in 16 times. Alternatively, if you recall from second year work, I suppose, to divide by a fraction, you can flip the fraction and change divide to multiply and get 16 over 1. An easier way to think of that, though, in the setup we've got in the question here, is just to take our denominator of the fraction, if it's on the bottom of another fraction, and bring it to the top. So you can kind of think that through in your head, and we're just doing 2 times 8 divided by 1, which gives us 16x to the power of a half plus c, and that is the answer. I'll just rub this out, get it out of the way. Looking at example B. This time it looks very similar, but there's a subtle difference in that the index is not negative. So we are integrating 8x to the power of a half with respect to x. So we take our 8x, we add 1 to the power, so a half plus 1 makes it 3 over 2, and then we divide by the new power. So we're dividing by 3 over 2. Again, in your head, you might be thinking of taking this 2 up to the top to make it 2 times 8 is 16, and then that leaves us 16x to the power of 3 over 2, and we've still got 3 on the bottom. Oh, I missed out the plus c back there, and we need to finish it off with our plus c. So that is the answer to that question. Okay? 16 over 3x to the power of 3 over 2 plus c. We could, if you preferred, you could write it as 16 over 3x to the power of 3 over 2 plus c, if you preferred that. What I definitely don't want to see people doing is writing it like 16 over 3x to the power of 3 over 2 plus c, because then it isn't clear at all whether the x is supposed to be on the top or the bottom. So I definitely don't want to see that kind of setting out for the answer. And of course I could have as well taken it further and changed the fractional index to something with a root involved in it. Look at example C. So this time we've got some subtle differences going on here to think about. So this time the first thing I'd point out is the different letter that's involved. We are integrating 12t to the power of minus 3/7 with respect to t. Notice the difference in the letter there. It's not x we're using anymore, it's t. The maths, however, is just the same. We need to take our 12t, we need to add 1 to the power, so minus 3/7 plus 1, or plus 7/7 gives us 4/7, and we need to divide by that new power, and we need to add c to it. So if I was working this out, I would be thinking, I might do it in my head, but I may not. It kind of depends how confident you are. I'm going to take that 7 to the top and make it 7 times 12 over 4 t to the power of 4/7 plus c. And then I'm thinking that the 4 goes into 4 once, it goes into 12 3 times. So the answer becomes 21t to the power of 4/7 plus c. If you're really good with your fractions, doing it mentally, then you might prefer to miss this out. If you're struggling with fractions, then you're going to find this a little bit tricky and you're going to need to get more practice. Let's look at the example D. Nearly done, it's quite a long video, this apologies for that, we are integrating 2 with respect to x. So that's a little bit strange, that one, because it doesn't have an x term in it, the thing that we're integrating. So to get around that, let's put it in. We could think about adding in x to the power of 0, because anything to the power of 0 is just 1. So if we do 2 times x to the power of 0, that's the same as 2 times 1, which hasn't changed it at all. So it's perfectly okay to rewrite it like that. The reason we did that was to get an x into it, which means we can apply our rule that we have for integrating, which is to take the function 2x, add 1 to the power, so 0 plus 1 is 1, divide by the new power, and add c. So the answer is just 2x. Okay? So we have gone through all of those examples now. What I would like you to do is work through these questions here. Indefinite integrals 1 and indefinite integrals 2. They're getting a little bit harder as you go through them. You can be selective, you don't need to do every single question. I would definitely want you to be doing the hinge point questions. Absolutely, and you should be doing more than that, of course. But definitely those ones. And when you're working on these ones, remember, when you've got something like this, you can just treat each part individually when you're integrating it. Just treat them as separate parts. So you're integrating the x squared, integrating the x squared, integrating the 3x, integrate the minus 2, and then just put your plus c at the end. Okay. Thank you for watching.